We've all seen the solar system pictures in textbooks, the sun slightly larger than Jupiter. But that isn't the right depiction of the scales. The sun is so massive that you could fit about 1,000 Jupiters inside. Impressive as it is, our sun isn't the biggest star in the universe or even our galaxy. That title goes to UY Scuti, and compared to it, our star is like a tiny pebble. But there's more. Scientists have stumbled upon something even more mind-boggling and enigmatic: a star with a black hole inside. It's an astronomical mystery that both puzzles scientists and could potentially explain how the universe came to be what it is today. But how is it possible for a black hole to exist inside a star? Why were these stars so gigantic? And what would happen if a black hole star wandered into the solar system? Stars are like cosmic blacksmiths. In their fiery cores, they're forging the majority of the elements we observe in the universe. However, the stars that could have existed at the very beginning of the universe were something different. Instead of conventional stellar cores, they harbored black holes within, allowing them to grow to unimaginable sizes and beyond ordinary. Stars arise from clouds of gas and dust. As gravity makes the densest regions of the cloud collapse, the resulting mass of material heats up and creates a protostar, an early stage in the evolution of a star. Eventually, the newly formed hot core accumulates enough matter from a surrounding rotating disk of gas, becoming a main sequence star that starts producing energy through nuclear fusion. It took our sun about 50 million years to reach this phase. The majority of stars will spend most of their lifespan as main sequence stars, but eventually, they will all either become white dwarfs if their mass isn't big enough or go supernova. After a star blows up, it can end up as a black hole or a neutron star, and the path it takes depends on how massive it was. When our sun runs out of hydrogen in about 5 billion years, it will turn into a red giant, expanding 200 to 1,000 times in size before finally shedding its outer layers and transforming into a white dwarf, a celestial object that's roughly 200,000 times denser than Earth but about the same size. This dense sphere will then slowly cool to about 10 million Kelvin, and in about 10 billion years, the white dwarf sun will crystallize. The process is somewhat similar to how water turns into ice, although the material is different. In the case of the sun, it will be carbon and oxygen solidifying. Stars over 10 times the mass of the sun will have a different fate. They're big enough for their cores to collapse after a supernova, but they lack the mass required to become black holes. Instead, deep inside these stars, the extreme pressure squeezes every proton and electron so tightly they merge to form neutrons. Neutrons cannot be compressed any further, so they counteract gravitational pressure, and the star finds a new balance. Neutron stars are the densest objects in the universe apart from black holes. They can be just the size of a small city, roughly 12 miles, 20 kilometers in diameter, but still have a mass of the sun. On Earth, neutron star material the size of a sugar cube would weigh as much as 1 billion tons, about as heavy as a mountain. But how do stars become black holes? While the star is still active, two prevailing forces work against each other: nuclear fusion and the intense gravity created by the star's own mass trying to squeeze it. Once there's no fuel left to power nuclear fusion, there's no longer a force to counteract gravity, and the star collapses in on itself, much like the controlled demolition of a concrete building. Einstein believed that anything could become a black hole if it had sufficient mass and was compressed inside a certain radius. Black holes keep on growing throughout their lifespan, devouring any material that gets too close. When this happens, the region where gravitational pull becomes so strong that nothing can escape increases, and the black hole consumes even more nearby material. It's somewhat like the sinking of ground due to the collapse of underground structures. Although with black holes, it is a gravitational sinkhole gradually accelerating as its event horizon grows. Normally, black holes have a limit on how fast they can expand. This happens because of something called the Eddington luminosity limit. Basically, it's the point at which a black hole can't take in material faster than it already does. If you were filling a car tire with air and it had small holes in it, the increased pressure inside would make some of the excess air escape. In space, something similar happens with rotating black holes. As matter spirals toward a black hole, it goes faster and faster. Because of this, about 42% of this matter can be converted into energy, and this radiation is so powerful it can push some of that incoming material away, just like a car tire pushes air away. This process is so efficient that the radiation emitted away surpasses the energy output from nuclear fusion in stars. Just imagine a future where we find a way to harness this energy and use it for our needs. Even supermassive black holes with a large surface area that attracts matter have this limit. They are at the center of almost every galaxy out there, and some of these supermassive black holes have been recently discovered to be much larger than we thought. That's one of the greatest mysteries in astronomy. The gradual accumulation of matter over the age of the universe fails to explain their enormous size. But there's something that might unravel the mystery. Black hole stars or quasi-stars must have been the largest celestial bodies to ever exist, dwarfing even the most gigantic black holes we've discovered so far. Today, the conditions of the universe do not allow black hole stars to form, but at the beginning of time, space was packed with massive gas clouds. Within these dense regions of space, material collapsed in on itself under its own gravity. Because there was so much more of it, it piled up, giving rise to baby stars of extraordinary magnitude. Although there's an idea that they may have originated from dark matter halos, invisible spherical regions of dark matter of up to 100 million solar masses, where thousands of supermassive stars could form. Normally large stars would go supernova and leave behind massive black holes. However, these celestial giants weren't just large. They were so huge their size allowed them to absorb the explosive force that would otherwise shoot the star's outer layers out into space. Instead, these ancient stars only experienced implosions, which transformed their stellar cores into tiny black holes while keeping the outer layers intact. If you could somehow observe this phenomenon from a close distance, you wouldn't even notice any changes with the star. Now that there's a baby black hole inside a quasi-star, it starts eating it from the inside. At this point, the black hole is tiny, but it's spinning, and this creates a disk of hot material circling it at nearly the speed of light. On top of that, there's no longer a limit on how fast it can devour gas as the star's pressure sends it straight into the black hole. The friction within the accretion disk becomes hotter and hotter, emitting tons of radiation and making the host star glow like a small galaxy. Quasi-stars, if they existed, grew faster than any black hole we've ever observed. Eventually, within millions of years, some of them would outsize the largest stars and black holes known today, like Stephenson 2-18, UY Scuti, and T618. Just how large is that? From thousands of times larger than the Sun to potentially even the diameter of our solar system and beyond. But this gargantuan size and mass also cause problems. The larger quasi-stars become, the shorter their lifespan. Our Sun has been around for over 4 billion years, with approximately 6 billion years left in its lifespan, while black hole stars lasted for just a few million years before spectacularly exploding with unprecedented power, releasing an ever-hungry monstrous black hole ready to drift across space in search of more material to gobble up. But what if a star like this wandered into our peaceful celestial neighborhood? Once a quasi-star found its way into the solar system, its gravitational influence would disrupt the established orbits of planets and celestial bodies. The once orderly planetary system would be in total chaos, with Earth experiencing a severe asteroid rain. The effects would start before the quasi-star entered our solar system completely. As the gigantic star swallows the outer planets and other celestial bodies, our planet would already experience a surge in temperature and luminosity, making the surface inhospitable until finally, it would consume the Earth too, although life here would long be gone by then. The central black holes within quasi-stars could have served as seeds for the formation of supermassive black holes that are at the centers of galaxies today. They might have even played a bigger role. The dynamic processes associated with quasi-stars, such as the collapse of the central black hole and interaction with the surrounding matter, could be potent sources of gravitational waves. These waves might have played a role in the formation of galactic structures and the distribution of stars within galaxies. But not just that, quasi-stars could have implications for astrobiology. The intense radiation from these objects might have affected the habitability of planets in their vicinity, potentially shaping the conditions for life in unexpected ways. That said, in the context of cosmic evolution, quasi-stars might have set the stage by shaping the early universe in unimaginable ways. But here's another mind-blowing thought. Although there are probably no quasi-stars in our universe today, tiny black holes roughly the mass of an asteroid from the dawn of time might still be here. Theoretical physicists speculate that if such black holes were abundant, They could be drifting around space, sometimes ending up trapped within gas clouds. They're as new stars are born, primordial black holes would eventually find their way into the star's cores. Even black holes the mass of Pluto would grow enormously within just a few 100 million years, a relatively short period of time in a star's evolution. So even our Sun could have one, which the late great Stephen Hawking once suggested. If it hit a black hole about as massive as Mercury, we wouldn't even notice it, although it's very unlikely. But there's one method scientists think might help identify such cosmic containers for primordial black holes. For one, the so-called Hawking stars would be much more long-lasting. To cool off, Hawking stars expand into red giants, something our Sun will do as it ages. However, red giants with a tiny black hole inside would be a bit cooler than they normally are. Researchers have already detected about 500 abnormally cool red giant stars. To find out whether these stars hide primordial black holes within, scientists plan to observe the stars' unique vibrations as they pulsate, which could signify they indeed aren't ordinary red giants. And here's another mind-bending thought. Some believe that the mysterious dark matter that prevails in the universe is, in fact, a swarm of miniature, countless primordial black holes. So while it's extremely improbable that a black hole like that would end up captured by a star, if there are an immeasurable number of them, at least some would. We'll have to wait until scientists figure that out for us. As we delve deeper into the mysteries of the cosmos, the concept of primordial black holes opens a fascinating avenue of exploration. These hypothetical black holes are thought to have formed just after the Big Bang due to high-density fluctuations in the early universe. They differ from stellar black holes, which are born from the collapse of massive stars. Primordial black holes, if they exist, could vary widely in mass, from as small as a few times that of an asteroid to several times that of our Sun. The study of primordial black holes is not just a theoretical exercise. It could provide crucial insights into the conditions of the early universe. For example, if these primordial black holes were indeed abundant, they might have influenced the formation of the first stars and galaxies. By seeding the universe with their gravitational fields, they could have played a role in the clumping of matter that eventually led to the formation of larger structures. One intriguing possibility is that primordial black holes could contribute to the mysterious dark matter, which constitutes about 27% of the universe's total mass and energy. Dark matter doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. If a significant portion of dark matter is composed of primordial black holes, this could revolutionize our understanding of both dark matter and the early universe. Current astronomical surveys and missions are designed to probe the nature of dark matter and its possible connections to primordial black holes. For instance, gravitational wave detectors like LIGO and Virgo are on the lookout for signals that could be attributed to collisions involving primordial black holes. These detectors have already revealed a wealth of information about stellar mass black hole mergers, but they might also uncover evidence of primordial black holes if they were common enough. Another fascinating aspect of black holes is their potential role in the evolution of galaxies. Supermassive black holes, which reside at the centers of most galaxies, might have been key drivers in galaxy formation and evolution. The presence of a supermassive black hole could affect the dynamics of the surrounding galaxy, influencing star formation rates and the distribution of matter. There is also the hypothesis that supermassive black holes might have formed from the merger of smaller black holes, including those that were primordial in nature. Exploring the life cycle of massive stars can also shed light on the broader cosmic picture. Massive stars, though significantly larger than the Sun, undergo a more complex evolution compared to their smaller counterparts. They end their lives in spectacular supernova explosions, which can lead to the formation of either neutron stars or black holes, depending on the initial mass of the star. These supernovae are not just destructive events. They play a crucial role in dispersing elements throughout the galaxy, enriching the interstellar medium with heavy elements necessary for the formation of planets and life. Moreover, understanding the diverse range of black holes, from stellar to supermassive and potentially primordial, helps us refine models of cosmic evolution. The interactions between these black holes and their environments provide critical clues about the formation and growth of cosmic structures. For instance, the way black holes accrete matter can lead to the formation of powerful jets of radiation and particles, which can affect the surrounding intergalactic medium and influence the growth of galaxies. The study of black holes and their interaction with stars also has practical implications for future space exploration. As we develop technologies for observing and understanding these extreme objects, we gain insights that could be applied to other areas of astrophysics and engineering. For example, the study of extreme gravitational environments around black holes helps refine our understanding of general relativity, which is fundamental to many technologies, including GPS systems. In conclusion, while the existence of quasi-stars and primordial black holes remains speculative, the exploration of these concepts drives our quest for knowledge about the universe. By investigating these cosmic phenomena, we not only enhance our understanding of the universe's past, but also pave the way for future discoveries that could revolutionize our grasp of fundamental physics and cosmic evolution.